So I didn't have the paper title this time at the beginning, but this slide deck is covers the paper MC-JEPA. So I think I have it open here. So this is the paper. Again, you have the same author as I-JEPA, builds on the same idea, but applies it to video. So the common thing between this MC-JEPA and I-JEPA is both are unsupervised learning strategies. I-JEPA is again unsupervised learning on unlabeled image data set. This is unsupervised learning on unlabeled video data set. Right? So solving the same problem statement for different data types and kind of inheriting a lot of the ideas. So again, the main thing that's talked about in this paper is self-supervised learning. And they talk about how the learning strategies which focus on content features, they do not capture object motion. And then again, optical flow estimation, which is a separate type of task than self-supervised learning on images. That focuses on how the pixels are moving. But there has been, like, where MC-JEPA comes in is it gives a solution for making the AI model understand both things. So the AI model trained by the MC-JEPA technique is able to understand semantic information in images, and it's able to do well on tasks that involve motion recognition, right? So like tracking an object in an image or in a video, let's say tracking a car in a highway cam or tracking a bike in a camera shot. The I-JEPA training strategy would not apply there because there is no aspect of like sending two images. There's no temporal input. So even if you train an I-JEPA model and I don't know, use the frozen embeddings to do instance tracking, it might kind of work, but again, it's not the expected application, right? So with MC-JEPA, what happens is, if you train the AI model as per MC-JEPA, and if you send an image, the embedding that you get is going to work really well on instance tracking. So tracking, this is the example. So tracking let's say motorbike across multiple frames. These kind of tasks can be really well done with MC-JEPA, right? But again, MC-JEPA is also just an embedding model, just like I-JEPA is an embedding model. So, like, does that make sense? Any questions?
Right. I'm able to follow.
Yeah, so I'm just trying to make sure I'm we talk, we contextualize MC-JEPA and I-JEPA separately. Both are embedding models, but apply to different data types, right? And where MC-JEPA comes in is like it uses the I-JEPA strategy of unsupervised learning or self-supervised learning on images, and combines it with a new optical flow learning task, such that the embedding model now also understands motion. So it actually captures motion information about every pixel in its embedding, in the embedding space. So that's kind of the novelty. So that's what is kind of written here. MC-JEPA, a joint embedding predictive architecture, which is the common property with I-JEPA, and self-supervised learning approach to jointly learn optical flow and content features, right? So it's able to jointly learn two tasks. One is how does a pixel move between frames? And the second is, are two pixels, do they share the same semantic information? Like, are both of these pixels belong to the same bike, right? Does the pixel belong to a bike? So all these kind of questions are captured by content features in the embedding vector, and the optical flow is the new thing that they're bringing. So they talk about different papers that have also which have also done motion estimation, but in a different way. They're not trying to capture pixel level motion. Neither they are trying to train an embedding model which just does well on image classification. but their models directly solve the object tracking problem. So if you apply their model, and let's say if you only have one person in the camera frame, then their models will create embeddings which would accurately track an object in the frame, right? And that's what they say. They learn features that are very specific to the tracking task. So again, using these ideas, you can build like a ball tracking model, person tracking model, but they have very poor generalization to other visual downstream tasks, such as image classification, object recognition. So a more reliable way to build is using visual representation is to learn multiple tasks at the same time. So I think I kind of remove certain words over there, but you'll get the idea. So this is just like where the current literature was as per the paper. And again, I'll take a pause here, see if there are any questions, especially I think if you're not there in the I-JEPA paper discussion, so I don't know if you would understand this. Yeah. So are things making sense? Like this is kind of the background research. That makes sense.
Yeah, more or less, I can follow what you're saying. I have the paper open also on the other side, so it's cool.
Cool. So let's just revise like the core idea in the I-JEPA discussion, right? So there are like 3 types of architectures. One architecture where again you have a data set with inputs and responses, or 2 inputs, and then in the joint embedding architecture, you embed both of them in an embedding space and learn some loss function on top of it to train the embedding space. And then there's generative type of architecture where after you create the embedding, you do not calculate the loss at the embedding space, but instead there is a decoder with a latent input, and that makes an estimate for the response or the second input, and then that's where the loss function is being created, right? So the second input or the response variable, they are not embedded when calculating the loss. That's the key distinction between these two. And then in the joint embedding predictive architecture, the loss is calculated in this embedding space, right? So it's basically like a union of these two ideas where the instead of calling it a decoder, it's a predictor, because again, it maps it to an embedding space, which visually may not, which is not human interpretable. And then in this embedding space, it also projects the second input or the response in the training set and then calculates the loss function on it. So these are the 3 types of architectures, and both I-JEPA and MC-JEPA follow this. So after this, I'm going to dive deep into the MC-JEPA paper.
So really fast on the joint embedding.
Yeah.
Or joint embedding. So one more. Can you just go over that one more time? Just it's been a few weeks.
This one?
Just the joint embedding predictive architecture.
Yeah. So here, just like imagine, right? If this is an image.
The predictive architecture.
Oh, this one. Okay. Yeah. So yeah, what happens is, let's say a practical application of this would be you run the image, get a 760 cross vector, right? Also project your, let's say out, like a image from the same category, right? And you would then also embed it in the same embedding space and calculate like an N2 loss or any loss on the embedding vectors, right? That's the joint embedding architecture. So it takes an idea from that, which is do not learn the loss directly on the input, but kind of project it. Now, what happens is in the JEPA architecture, you do not directly calculate the loss on the projected vector, but instead it's combined, or in a way you can say this is a type of regularization, because this is noise. You can actually change at every iteration. So in a way, this regularizes the X sort of at a data augmentation thing at a really low level, at an embedding level, if you can think like that. And once you have projected the input image to, let's say, some embedding vector, again, you project it to a new embedding space. And then, and this new embedding is in the same embedding space as your Y encoder, right? So technically, the dimensions here and dimensions here should be the same, because if they are the same, then like the X encoder and Y encoder can actually share the weights, right? That is really useful if your X encoder and Y encoder share the same weight. So if they share the same weights, which means this output dimension and this output dimension has to be the same, right? But again, there can be some, you can use different encoders, but that's kind of the overall idea, right?
Okay.
Yeah, it's a union, right, of these two things.
And I guess the thing that I'm remembering from the paper was there was, with generative architecture, they would, you'd maybe have an image that was masked, right? And you try and predict a section of the image during training, and then compare it with, the embedding of the full image, right? Yes. And then for joint embedding predictive architecture, weren't they saying they'd split it up into, say, like 9 chunks, and then you'd only get 1 chunk in the X, and you would try and predict all of the other 8 chunks from that? Is that how it works?
Yes. So that's kind of completes the I-JEPA idea. So what the first thing that you mentioned, right? Those are the advantages of this architecture. You do not run into collapse, right? Embedding collapse, because here, in generative, this would be an image, right? So this will be high dimensional. And again, this decoder is also creating an image, right? So here kind of you're in a sparser output space. So there can be a dimensional collapse. That's one advantage of operating in the embedding space, right? Because the dimension of SY would be much lower than Y, right? That's kind of the, I think, one advantage you talked about. And what was the second thing? You said something else as well.
I think, well, I just want to be clear on, so X encoder would take in a small or chunk of an image, for example, during the training, or just in general, it'd take a small chunk of the image that was split into 9 different sections or something. And I think you would have a different chunk every time or something like that, right? Throughout the training, and then I wasn't sure I don't remember what Z is. Is Z like the masking in generative?
Correct.
Oh, so they'll take the chunk of the image, so they'll take a bunch of different sections of the image, and they'll also mask it in different ways.
Yeah. So this you can,
and then the output is a prediction of where it is of all the other 9 sections, essentially.
Yes.
Is that right? And then what does this Y encoder do for joint embedding predictive architecture in that case?
Yeah. So then what it does is you have, from an input image, right?
Yeah.
You kind of create, let's say, 9 crops, right? 9 boxes.
Mm-hmm.
So you take the first box, encode it, right, into an embedding vector. And then the embedding that's being created, right, at this point, that's used by a downstream model to predict the encoding vector of a different, a different crop in the same image. Or it, so it's
is Y encoder encoding the different crops
as well. Yes. So this is encoding the target crops. This is encoding the source crops. They actually share the same weights. And then in SY, like the embedding should come out to be same, right? Because those crops are coming from the same image.
Oh, okay. I think that's what was confusing me. So X encoder and Y encoder are actually the same weights. But there's this second model that's taking the weights of X and trying to predict the rest. And then you're comparing that with the actual encoding of the other 8 sections, for example. In the same way that generative would, you'd encode an image, you'd have you'd have something that decodes the masked version, and then Y would be the same. Y would just be an encoded version of the unmasked image, right? And you would be comparing.
Yeah.
Oh, okay. That makes a lot of sense now. I was confused by this X encoder, Y encoder.
Yeah.
Yeah, sorry about that. Thanks for going.
Yeah, I mean, I also read it as X1 and X2. It makes no sense.
Yeah. And then for joint embedding, just last thing here. For joint embedding, so you take 2 images and then you're trying, I know like conceptually, I think you're trying to determine how close or far apart they should be in the embedding space. But how does that actually, how do they check? Yeah, like I guess with the joint embedding predictive and with generative, there's a checking process, right? With joint embedding, it doesn't seem like there's a checking process.
Yeah. So if you can see this image, right? This is from the IJEPA paper. This is what is happening, right? The loss is being calculated over here, right?
Yeah.
So the context encoder kind of maps to X encoder, right? And the Y encoder maps to the target encoder. So then basically like different parts of the context are run through a predictor model, and then different parts of the target are run through the same encoder model, and then you calculate the L2 loss, right? But again, the big advantage over here that helps avoiding the collapse is this L2 loss is being calculated at an embedding vector level versus in generative that's happening at an image level. Yeah, so that's almost like a reconstruction loss versus this is like embedding loss.
And then for joint embedding, it looks like there's 2 encoders that also have the same weights.
Right.
But this would be a joint embedding predictive architecture, right? So for just straight joint embedding, it doesn't look like there's the same check phase.
There is, right?
Or red there, I guess. Okay, cool.
So yeah, I think that was nice. Like it's a pretty quick deep dive on IJEPA. So I have a list here of things that we will cover. I think these are concepts, even kind of on which MC-JEPA builds on. So I'll go through them in some order so that we kind of establish that you understand these concepts, because they are really important for me to explain the MC-JEPA architecture, right? So, but again, I think we are now getting into the MC-JEPA territory, which is what is MC-JEPA's architecture, because again, this is the training flow for IJEPA. MC-JEPA has a completely different training routine. But before I go to training routine, there are some concepts that they have talked about, which are common across AI model training or like image featureization. So we'll cover those first. So let's start with 4D correlation volume. So in this, so if your AI model uses a 4D correlation volume, essentially then what's happening in your architecture is you have one image that's featureized, right? So for every kind of crop over there, you have a feature vector. That's something that IJEPA also does, right? And then for a second image, similarly, you kind of break it down into a grid, and then for every grid, you have a feature vector. The most efficient way to do this is by using a convolution filter, right? So convolution filter exactly do this. They kind of take a box and then project it into some embedding, an RGB image through a convolution, and get basically this 3D map where it's W cross H cross E, E being the size of your embedding space. And if you have two such maps where of W cross H cross E being the embedding space dimension, then for those two embedding spaces, those two features of two different images, they are combined to create a 4D correlation volume, right? So this gives you idea about the correlation between the different embedding vectors in the two feature maps, right? So the fourth dimension, the reason it has 4 dimension again is simply because of this, where you take every embedding from image 2 and you take a cosine or a vector to scalar function between the feature for this part of the image and feature for this part of the image, and record some scalar value, right? So then for every H cross W dimension, like for every channel value, you will calculate H cross W numbers using the feature map 1. So that's where the 4D volume comes in. I'll take a pause here and just make sure if there are any questions I can address. When I did not contextualize this, like this is actually part of a neural network architecture where that's where you will run through it. So yeah, please, if there are any questions or if you understood it, let me know.
And take the part for each pixel, those are of calculate. We do pixel to pixel mapping and get the same distance of the embedding level.
Yes.
Yeah, I mean, the contextualization, like how it's going to be related. It's like optical flow, in that many talk.
So this is me just trying to make it more relatable. Well, that's where this would happen, right? You take an image, right, through a convolution filter, you get this feature map, right? So this is the feature map that comes from a convolution filter. And this is the second feature map from the same convolution filter on a different image. And then you can take both feature maps and create a correlation volume. So
create a correlation volume.
So just remember this term because it can come up, right? And the idea is very simple. You're just taking cosines. Just taking cosines between two vectors and storing it in a, H cross W, like a 4D map, because, yeah, I think you get it. So now let's move on. The second concept is that of flow and warping, or kind of optical flow. So I don't know if you have come across optical flow before, but optical flow is basically figuring out pixel correspondences between two images, right? So for example, these are just two different images where these two pixels have been identified as being part of a correspondence. And then identifying these correspondences is something you can do with a flow map. The flow map basically says that a flow map for an image basically says that for this pixel, in the next frame, where is it going to go? Is it going to go in this direction, or will it go in this direction? The flow map basically gives you, velocity in both these directions. And then based on that flow map, you can warp an image and create like a new visual, right? So in this case, the image has been tilted. So that's what warping means. So if you have a flow map, then you can warp the image. And the flow map is estimated using different algorithms. These are the optical flow estimation algorithms. So that's what optical flow is all about. And this is a simple example where, you can even create image filters using flow maps. This is like a swirl warp, which just means that instead of predicting the flow map, you are applying like, this is the swirl flow map. So you can imagine this, right? Like it's basically applying this map on this image, and then it's warping it to create this effect. Any questions on this, on optical flow image warping?
Like I remember, I have seen optical flow maps. So basically the velocity warping. Now, when we combine it with the image, the warping part is something I'm still trying to understand what is happening.
So warping is simple, right? So see, warping, this is the warping algorithm. So again, there are two types of warping algorithms, forward and reverse. They only make sense if you're talking about videos. Like in this case, there is no forward and reverse warp if you're applying it on images, because there's no sense of time. So essentially, this is the warping algorithm. And what you do is like for every pixel location, for every pixel coordinate, the optical flow model, which in this case is FNG, it gives you the new location, right? So now you kind of take the color value, let's say here, and you map it to this location, right? Because that's what the optical flow map, right? It would have a direction like this.
Right.
So you're basically displacing pixels as per the optical flow map. That's what warping is.
Got it.
So let's, so after this, we just covered 4D correlation volume, we covered warp. These other concepts are pretty, I would say, specific to the paper. Kind of, they have their own already in defining these ideas. So before I jump into these concepts, I'll talk about the related work that's given in the paper. And that will give some idea about like, what are their ideas kind of built on. So just in the field of self-supervised learning, which is where I-JEPA is also, right? These are the ideas that are listed in the paper. So one way to do self-supervised learning on images or videos is to handcraft data augmentations. And again, after applying handcrafted data augmentations, this could be your input, this could be the handcrafted data augmented X, and you would learn the embedding space, which minimizes the distance, between the embedding vectors of these two images, which are only different by your data augmentation. So that's one way people have attempted self-supervised learning, because if you just have unlimited labeled images, you can start running data augmentation on them and actually train a joint embedding architecture without any labels. So you kind of succeed at self-supervised. The second idea they mention is contrastive methods. So this just talks about triplet loss, center loss, all these kind of techniques where you almost apply physics to the embedding model and say that, okay, these two things should be far away in space, these two things should be closer together, etc. The third type of idea that people use in self-supervised learning is clustering methods. So if you have some kind of categorization for your embedding, like some kind of topic assigned to every embedding, and you kind of know the balance, right? Like how in space they are distributed, like one category, if all your categories are balanced, which just means that, you know the relative sizes of each of these categories, then you can use that to inform the loss function when training the embedding model. So that's kind of the third idea they mention. Fourth idea is not using contrastive methods. So not using pull and push physics related methods. But when you don't use that, collapsing becomes an issue. So then these ideas generally come with some architectural tricks. The next idea they talk about is covariance-based regularization, which is in a way, you try to keep your set of parameters tight. You don't want them to be highly correlated. Neither you want the absolute variance. This actually just talks about covariance. So I'll take a pause here because variance loss is something that they talk specifically in this paper. But covariance just talks about, keeping your features informative. And then the fifth idea that they quote is using masking and patch reconstruction approaches, where I think Oliver mentioned this, right, 2 slides back, is you take an image, you apply a mask on it, and then try to learn an embedding space in which both the masked image and the unmasked image have a low loss value. So these are the different ideas in self-supervised that this paper builds on. Any questions here? Well, I'll move on to this optical flow. So the second domain they touch upon in the paper is optical flow estimation. So again, in optical flow, as we talked about, you're basically estimating the displacement of every pixel in the X and Y direction. So people often kind of bring in a smoothness term to make sure that the model does not predict like a large displacement all of a sudden, right? Because of some noise in the training data or the points where the parameters are. And then I think here because they are no longer in the unsupervised or self-supervised domain, they talk about the fact that in optical flow, people have used, supervised learning and convolutional neural networks. I think that's kind of the main idea. But the problem with supervised learning, as they talk about, especially with respect to optical flow, is that it's all done in synthetic data, right? Because if you take real camera footage and get that labeled, even by a human, it will be like a law. It's going to be a very slow and long task. Someone sitting and kind of creating pixel correspondences. But creating pixel correspondences becomes really easy if you're synthetically generating the data, because whatever rendering engine you use, whether it's Blender, whether it's Unreal, these renderers know exactly how the pixels are moving. So with synthetic data, solving the optical flow problem becomes a lot easier. So that's what a lot of people have attempted. The fourth idea is photometric consistency. Here, photometric consistency just means that they use the color channel values, and I leave it to that because again, it's not like a big part to understand the paper. And then they talk about, a lot of different data augmentation tricks and like very special knowledge about the optical flow problem to increase the training samples. So these are the different ideas they talk about in the related work section. I'll take a pause here and see if there are any questions about optical flow.
Really cool. Since you mentioned that one is supervised learning is focused on synthetic data, right? So how do they do that in MC-JEPA?
How do you create what?
So in MC-JEPA, how do they do the optical flow estimation on G1 data? Do they also work in the synthetic data?
So on general data, how to do training of optical flow on general data?
Yeah, I was talking in respect to MC-JEPA.
Yeah, can you repeat? I'm not, if you can speak louder, I'm not able to hear properly.
Okay, that's it. Hello?
Yeah.
In respect to MC-JEPA, do they talk about how to train on generic data?
Yes. So MC-JEPA's learning strategy can be applied on general data, right? So that's like a huge advantage they have over people proposing, learning optical, who are solving optical flow on synthetic data. Their idea can be applied to, real camera footage. Let's talk about this final domain, which is multitask learning. So this is another idea they bring in the MC-JEPA paper, which is when you use the same embedding vector, when you train the same embedding vector on different tasks at the same time, right? So every time you calculate the gradients on the parameters, if the gradients are calculated based on multiple tasks, then the model is able to learn better. That's the idea. And in MC-JEPA, especially they use the shared representation between image data and video data. So their model actually works on both images and videos. So if you have an image of something, you can re-ID that thing in multiple videos. And then they talk about how MC-JEPA uses multitask learning for self-supervised content features. So this is basically the summary of MC-JEPA. I think I put it here again, but just a refresher before we kind of go deep into now MC-JEPA is MC-JEPA is essentially a multitask learning technique for self-supervised joint embedding predictive architecture. And the multitasks basically capture content features. So if the multitask is interpreting the semantic information in pixels, as well as predicting the flow of every pixel, right? Where is it moving in the next frame? So I'll take a pause here to do a quick review of this part. So we captured 4D correlation volume, understood that, covered warp and optical flow. And now we are going to go into all of this. But before we kind of, do a deep dive on these things, we have covered the related works. So a lot of these ideas are, will be revisited. So, let me actually talk about this slide and then take questions. Just to again connect this with I-JEPA, I-JEPA is another embedding model which projects your images into to a vector. MC-JEPA also does the same thing, but MC-JEPA is trained on a multitask loss, which also expects it to learn the motion of a pixel, right? Between if it was part of a video sequence, right, or a frame sequence. So that's the new thing that MC-JEPA brings in. But MC-JEPA is also just another encoder model, right? So it's also just projecting images into an embedding space. That's all it is doing, right? So this is the MC-JEPA encoder that we'll go over the training for, we'll go into its architecture. But this essentially is the MC-JEPA model, right? So the MC-JEPA model, before it is trained on the motion tasks and as well as semantic understanding tasks, the model is pre-trained, right? So the model is pre-trained on images from ImageNet, and again, any image data set can be used. So what happens is, like, you run the image through the encoder, get the MC-JEPA embedding vector. There is a VC regularization loss. We'll cover that later. We can ignore that for now. So you calculate the MC-JEPA embedding for your image. Then you have a second model, which is almost like the predictor model. You can say the predictor model increases the size of the embedding vector. Again, the VC regularization loss is captured. We'll cover this in the next few slides. And once the input vector is expanded, there is an N2 loss that is calculated on them, right? And this core training objective is called SSL, that's how I'll refer to it in the rest of the slides. So this SSL training objective basically means that on an image data set, you're running both, you're taking an image, you're taking its augmentation, which in the paper they talk about random cropping and color jittering. You take the input image and the augmented image, run both through the encoder, calculate a new loss, run both through the expander, calculate another loss, then finally calculate the L2 loss. And if you sum up all of these loss values, then that's your SSL loss. And this is used just to pre-train the encoder. So any questions still here? I think you've now already entered the training territory.
And the goal here would be you have two different variations of the same image and you try to minimize the difference in the embedding.
Yes.
Why have an expander? Like, what is the expand? Is my understanding of the embedding space, you take an image, or you take something in high dimensions, and then you're kind of reducing the dimensions, right, with the initial encoder. What is the expander's kind of doing the opposite of that, right?
Yeah, and they don't talk about that in the paper, so I looked it up. There was something. So if you check here, it's then mapped to an expander network on which the PIC reg loss is applied, and they do not give any reasoning into why they bring in this expander network anywhere in the paper. As you can see, this network is mentioned only once.
Was this image from the paper that you got, the image that you showed in the slide?
Yes.
Maybe it's, if you look the image, it doesn't look like, you look view 1 and view 2, they both don't have the entire image. So perhaps the initial encoding is just, or encoder is encoding the segment of the image that they have, and then the expander takes that segment and tries to expand it to predict the entire image.
No, that's IJEPA, right? So that's not done here. Here it's, so that much is pretty clear in the paper.
Okay.
Yeah, they do not give details on the expander network, but yeah, there is no cropping of the image, right? I mean, you're not trying to predict patches in the same image using other patches. Here it's a simple content learning routine, right? Where you run the image, get an embedding, run it through the expander, get an embedding, and you calculate the N2 loss. At the same time, this variance covariance loss, variance covariance regularization loss is being captured. I'll go into it. But in a way, that's a regularizer, right? So this is the mean loss function, the L2 loss. And why do they apply L2 loss after running it through the expander and not here? They don't give any reasoning in the paper. This slide again basically talks about the beginning of the training routine, right? The training routine begins for videos, right? So just to kind of clarify, this is the pre-training done of the encoder on images, right? Mm-hmm. The encoder is trained, and then in the next step, you move on to training the encoder on videos. Right? And essentially, videos are image sequences, right? So what happens with video, when training on the video data set is instead of just using the final output of the encoder, right? Here, as you can see, X1 is the final output of the encoder. When it's about training on videos, the intermediate levels, right? The intermediate feature maps in the encoder are also being used. That's why it says the encoder produces a set of pyramidal features, which basically means that, you have the intermediate levels of the feature maps are also taken out from the encoder. And then you have basically these two pyramids, right? So essentially now you have, these two pyramids. This is like, convolution layer 1 output, convolution layer 2, convolution layer 3. So at the final level, the final at when L is equal to L, like the biggest level, the features in the feature map, they are more coarse, which just means that they map to a lot more pixels in the actual input image. So I hope this makes sense. The pyramidal feature is a key idea, so just keep that in mind, right? So when we trained on images, we did not use the pyramidal features, we just used the final output. When we are training on videos, we are actually using the intermediate outputs of the encoder in the loss functions.
So I wasn't super clear on the term pyramidal features.
So pyramidal features are like this. So this is your input image. This is H cross W, right? When you apply the convolution filter for the first time, right? It operates on, these many images, right? So you basically, let's say let's say that you get a H by 2 cross W by 2 feature map, right? So if you apply a convolution filter, you're essentially downsampling your input image.
Yeah.
Right. So if I apply multiple convolution filters, right, then at the end, this one embedding vector, and again, this is how it works, right? The convolution filter maps it to some embedding space. So it does pooling, and then you map it to some embedding space, right, of dimension E. So if I keep applying convolution filters, I'll end up with just like one embedding vector, right? Does this make sense?
Yeah.
Right. So if I keep applying convolution filters, so go ahead.
This would be the core, because they mentioned they start with the coarse version and then they move to more fine grain. So the coarse version, they would apply a bunch of convolution filters.
Yeah. This is fine. This is coarse.
Okay. And then that whole thing is, interesting. I didn't realize that whole thing was captured into a pyramidal feature.
Yeah. So then you kind of take all of these things and you make a pyramid.
Right.
So
okay. So you're saying there's a bunch of features in the image, and you have, a vector for the initial for each feature in the initial convolution, and then the next one, and the next one, the next one, all stacked together. And would it be a pyramid for each feature? It wouldn't be that, right? It would be a pyramid for a bunch of different. It would just be a pyramid for the different convolutions, and it would just be a pyramid per image, right? Just a pyramid per image. Yes.
For every image, you create one pyramid, right?
Okay.
And then when training on video, you will take adjacent images in the frame sequence, right? So image at time t and image at time t plus 1. So for each image, you have one pyramid, right? So now you have two pyramids, right? And this notation, x of L, it just means that at level L of the pyramid is the feature map that they're talking about. Right. So these are different levels. So I think it's easier to understand top down, especially the loss function. So I'm going to try explaining that and then go into the loss function specifically. But again, for training on images, it's very simple, straightforward. It's just an L2 loss and a VC regularizer. And that's all that they are doing in pre-training. All the complexity actually comes in when training on videos. And that's when the multitasking also comes, because as you can note here, this is not multitasking, right? This is joint embedding architecture, where you have X1 and X2 and you're projecting both to some embedding space and calculating NL2 loss. So this is just joint embedding architecture. So this is not even JEPA. This is where JEPA actually comes in, and this is where multitasking comes in. So when training on videos, it's not done just on videos alone. At every iteration of the main training routine, what's happening is you sample a batch of images from ImageNet and calculate the SSL loss, right? So, which is this loss, right? So at every training routine, you get a batch of images from ImageNet, calculate the SSL loss, and then take a batch of frame sequences from the target video, right? And compute the flow loss. And, we'll go deep into this later, but kind of the core idea is that once you take a set of sequences from a video, for every sequence you pick out adjacent frames. For every adjacent frames, you calculate 2 pyramids, and then those 2 pyramids are used, to calculate these different losses, right? So every pair of such pyramids, the loss for every pair of these pyramids is summed up for the set of sequences, and then you add that loss to the SSL loss, and then kind of backpropagate the gradients, right, into the different parts of the architecture. The encoder, which is shared, which is shared between the image training and the video training, the expander, which is part of just the image training, and the flow estimator network, which is just part of the video training. So there are 3 pieces of architecture. We have already seen 2. The third one is going to come now on the next slide. But all 3 models backpropagate gradients from 2 different tasks, from the video task and from the image task. And that's what makes it multitask. So any doubts about this, about the high-level training routine?
You mentioned that image training is happening first. Or is it happening simultaneously with the video training? So that's, backpropagating together, it has to happen simultaneously.
So the image is also, the model is pre-trained on images and then jointly trained on images and video.
Okay. Right. So how is that pre-training beneficial? Like, can't we just do a joint training together?
Yeah. It's not clear to me either why they, so if you use a pre-trained self-supervised, so they use a pre-trained self-supervised model on ImageNet and then train the flow estimator on it. So they clearly state that they do pre-training, but again, they don't mention why specifically they do this. And why not just do this training at, straight? I think it kind of beneficial because, this is just giving the encoder a chance to learn that this is a dog's eye, this is a dog's eye as well, without having to focus on motion. And learning motion, as you can see here, the fact that they are kind of backpropagating errors on, the intermediate levels in the encoder, it just means that it's a more difficult task, right? So it's a simpler task that they train the model on, maybe get it to an initialization point. And then this is almost like a fine-tuning step, right? But nothing is frozen, but it's like a second task.
Okay, that's it. So the pyramidal features are coming from the same encoder, right?
Right, yeah. Just picking out the intermediate levels in the encoder.
Did we talk about the expander architecture in the video? No.
Yes, so they don't talk about it anywhere.
Okay.
So you can see it's actually, they have mentioned it here. So my bad.
Okay.
The expander architecture is a fully connected network with dimensions this.
Okay.
So this is the expander. And maybe, here the encoder. The encoder is upon the next architecture with 21 million parameters. And it produces a set of parameter features with 6 levels. and a resolution that doubles between each level. So these are the architecture details. You're able to see the screen?
Yeah.
This encoder details the paper.
Yep.
So I think this answers your question, right?
Yes.
Cool. I think will soon be done. I think now the rest of it is, separate ideas that you can easily piece together. So like we talked about, here we have this VC regularization loss. It's a pretty good loss to regularize the features that are produced by the encoder. Right, as you can see here, whatever feature map is finally created by the encoder, as well as the intermediate features that are calculated by the encoders, the pyramid, the different levels of the pyramid, both of those feature maps are regularized using this VC loss. And as you can see here, the VC loss basically ensures that the magnitude of any of the features on their own does not jump, too high, more than gamma. Up till gamma, it's okay. And then you also have this covariance loss that, the empirical covariance matrix, which I think they have picked up from, if you remember, I think this slide, covariance-based regularization. So this is kind of the corresponding paper is from where they picked up that idea from. And I think the core advantage is this law helps stabilizing the training with multitask setup. So especially in the video training routine, this loss really helps them to stabilize the gradients. The second type of task is second type of loss that's used in the, this one. So we have already covered this. These three are related. So I think essentially, when actually all these four are related, these are all of these are related to optical flow task, flow estimation. And these are very much related. So we just first covers L cycle. So the cycle consistency loss can be understood simply as, this F is your optical flow map. So once you have an input image, you have a set of pixels. For every pixel, the optical flow estimator tries to predict the X and Y displacement. Now, in the cycle consistency loss, what happens is like for your image at time t, you calculate the flow for forward warping, and then for image at time t plus 1, you use that image to predict reverse warping, right? So what would happen if we move back in time, right? And then both of these flow values are applied, because essentially what's happening here is that t is moving because you are applying the flow model in the forward direction. Xt becomes an X gap estimate, right? So do it here. So so this basically is X cap p plus 1, and then you would take X cap p plus 1 and then do reverse warping. So then this whole thing becomes like an estimate from an estimate that estimates t, and then you take the loss value between these two, right? This is just an L2 loss. So this is the cycle consistency loss. It just makes sure that the model does not predict hugely different flow maps for the image at time t plus 1 or the image at time t. Like both of them, time t plus 1 and t, both flow maps should maintain this cycle consistency. So that's the idea. I'll cover one more slide. I think then it will make a lot more sense. So this is how the flow estimator works. As we have talked about, Xt comes from the encoder, right? So you have an input image, you run it through the MC-JEPA encoder, and once you have that MC-JEPA encoder, you pick up an intermediate level in the pyramid of that image, which is L. And then here what's happening is the input vector is being applied along with the estimated estimated MC-JEPA embedding vector for time t+1. So this is the actual embedding from MC-JEPA for the frame at time t+1. This is the estimated. You calculate the correlation volume between both of these two features, and then you pass on the flow map from time t, and then whatever is the residual flow map, that's being predicted by this CNN architecture, right? So you have 3 inputs and 1 output, and this is a residual prediction, right? So what's missing in this, or how does this change for, for in time t+1? So yeah, and this is again the difference, as you can see, is between levels, right? So whatever the flow map is coming for level L, what's the residual for level L+1, right? So the residual is being calculated across higher and higher levels, if that makes sense, right? And if you look at this bigger image, I think the whole thing would be more intuitive. So you have, and we can actually do this, where, yeah, you have an input image, right? The input image is mapped by the, by the MC-JEPA encoder. So, encoder. Yeah. So the input image goes through the MC-JEPA encoder. Then, you take the intermediate levels from the encoder. Or maybe a better way to understand is like you get the pyramid, which maps to different levels, and as you go from 1 to L, you're basically going in this opposite direction. This is the opposite direction. So you take this, you run it through the flow estimation network, which is this. So the first level of the pyramid, this one, it's passed as input to the flow estimation model. After running through the MC-JEPA encoder, you pass the value 0 matrix, and then the additional thing that's being passed is for the adjacent frame, right? So for the first frame in the video, this would be 1. So you take, this would be 2. So you take the first frame in the video, run it through the encoder, get the embedding, send it to the flow estimation architecture, take the second frame in the video, also send it to this flow estimation architecture and pass the 0 vector map. And once you have those two things, then you calculate the residual, right? And the residual, because in the first frame or the first level, it is 0, you're calculating the first flow map for the routine. And this happens iteratively until you reach the 6th level as per the architecture given in the paper, or any number of levels, right? You can make the convolution model deeper and the convex model deeper and deeper. So that's what is happening. And every time you estimate the flow map, you apply a warp function, and the warp function is essentially an addition, like forward warping. And once you have warped it, you get an estimate, right? So for level 2 feature map for the image at time t, you get an estimate of how does that intermediate feature map should be displaced to calculate the equivalent feature map in the next frame of the video, right, at time t+1. And you take that estimate and you take, you pass the actual image in the second frame of the video or the next frame in the video, calculate the encode embedding, and then you also create an estimate using this flow architecture, and then you calculate a regression loss. So I should surely take a pause here. And this is the regression loss, right? So, but the regression loss is super simple. It's just an L2 loss, right? Yeah. Please, any questions about this? Because this is really also the crux of the paper. This is like one of the core ideas. Yeah. Like, this flow estimator makes sense. Like, you can see where this fits in. Like, this is this model. And this is essentially the video training routine, right? So you can see how different this video training routine is compared to the image training routine, right? Which is talked about here. Image training is super simple. It's still an anti-gloss, but there are only 2 models. When you're training your encoder on the videos, you're basically, so this is the encoder, right? This whole yellow thing is the encoder. You introduce this new trainable model called F theta, right? Or the flow estimator. So in the video training, this is the new thing. In image training, it's the expander. The MC-JEPA model is this encoder, this yellow thing.
And before when the pre-training starts, because this is during not pre-training, sorry. So this is at every step of the training. So before it's been fine-tuned at all, it's just going to go through the same encoder that it would have as the output of the pre-training, right?
Could you repeat the question?
Sorry, you said there was an encoder and the F theta was similar to the expander in the previous architecture, right?
Yeah, it's not similar in architecture, and we can actually quickly see that. We should have enter. Flow estimator architecture, flow estimation. Yeah, it is a layer. Yeah, I think, yeah, this is the backbone. I see. Yeah. Well, yeah, so the flow estimator is also convex. Right. So, yeah, but I think we should double check that. I didn't know what architecture Flow was using. But what I mean is that there is correspondence, right? So when you're doing image training, you're essentially training this extra model called expander, right? Which is only useful for training, right? So once your training is done, you throw away these weights. They are not useful anymore. The thing is true for the flow estimator, right? Like post training or like unless you're fine tuning the model, during inference, you do not need this. Right? During inference, you only need the encoder. Right? Unless you want to like predict the optical flow map, then you definitely need this. So that's kind of the correspondence. That's why, I mean, I say over here that, we are training 3 things, right? So, we are back propagating the gradients through the encoder, expander, and the flow estimator network.
And then over time, it would just be the encoder, right?
Yeah, and only the encoder architecture is shared between the 2 tasks. Right.
So, yeah, okay, got it.
So these 2 are not shared between the 2 tasks.
This might be basic, but I'm just trying to understand how how you go from the pre-trained version to the at the end of the pre-training, you have an encoder, right? You throw away the expander, you have an encoder with solid weights, and then you're moving from that to a new encoder that incorporates both movement and context, right? After pre-training, you have context of the features in the image. You're trying to, and so I'm just wondering, like, in this architecture that you're showing right now, you're starting with, before you do any fine tuning, you're starting with that encoder, right? And then you're adding the F theta as a step or something like that. And then you're back propagating to adjust the weights of the encoder, right? And where is the encoder in this? Is that in this here? That's that top layer?
Yeah, the yellow part, right? The yellow part is the encoder, right? So,
and what are these layers here? What are these XTL? Sorry.
Yeah, so the L
These little layers of the pyramid?
Yeah, the level in the pyramid, right? So
Okay.
The encoder is a convolution network. So, and if you remember the coarse and the fine, right? So this is the coarse, this is the fine. Right? This is the
So because the encoder was only trained on one image, so with the encoder, or the encoder wasn't trained to take a pyramid as an input, right? It was just trained to take one image. So would it be ran on each individual layer of the pyramid?
No, so the encoder creates the pyramid, right? So the encoder is the pyramid, right? So see what's happening here is,
Oh, got it.
right? Here you're just getting the final output. But in the video encoding, you're taking the intermediate levels, right? The intermediate channels. So that's how you get the pyramid.
Oh, okay. Got it.
So this semicircle kind of expands into a, they have kind of stretched it into like a pillar or something, right? So that's what it
So
is.
the encoder creates the pyramid. Okay, got it. And then it creates the pyramid.
Yeah. Does this make sense? Yeah. Once it creates the pyramid, then you iteratively take every level of the pyramid, take the output of every level, and then you estimate the flow map using the flow estimation network. And then you take the equivalent level, right? So level 2 in the image at time t, you take the same level 2 for, same level 2 of the pyramid for the image at time t plus 1 from the video. And you calculate the regression loss on it. Right? So if level 2 of the pyramid at time t, if it can really predict well, level 2 of the pyramid at time t plus 1, right? Then that is minimizing the regression loss, right? So in a way, you can think that this is like the I-JEPA equivalent, right? So I-JEPA is just iteration 1, right? Because in I-JEPA, you only calculate one embedding and train the loss. Here, for every level of the pyramid, you're calculating a separate loss value. And you're summing it up across levels.
And for, just to clarify, so XT1 would be, let's say, like the highest level of, or the most coarse level of, so it's going to have a bunch of features, right? But just a coarse set of features. And you're comparing that to X1, the next frame, basically, right? This same level coarse, the next frame. And then you're trying to put those both into F theta, and F theta is trying to calculate how much all of the features have moved, right? Not just one of the all of the features,
all the pixels, right? So this,
or not pixels necessarily, right? Because it's gone through a bunch of convolution.
Right.
And then what is this F2 t plus 1? Oh, that's the output. That's the output.
Yeah.
F theta.
Yeah.
And then the warp phase. What the warp phase was something like you're trying to
just add in, right?
You're trying to add this to see if you got the correct
right location.
Okay, so you're taking the variances from F2 t plus 1, and then you're adding it to the features in the next layer, and trying to see, that's what that warp phase is, and then you're trying to see, was it correct or not?
Yep. And the key distinction between warp versus what happens in convolution is the warp, if you remember, it's happening on the pixel coordinates, right? It doesn't happen on the values themselves, right? So warp basically takes the pixel coordinate, right? So the flow estimator says that X and Y are going to become, if I take the X and Y coordinate, it will move in this direction. So that's what warping does, right? So warping essentially, when we come over here, warping is taking the coordinate, it's taking as input the coordinate of the feature values, and then displacing them, right? So it does not actually operate on the channel values. It does not operate on the value themselves, but it just kind of moves the pixels to a new position.
Or in this case, features, right?
Yeah, features, correct. Or it's moving the features to a new position, right?
So what is X hat to? Sorry, what is X hat?
So see, if you have level 1, right?
Yeah.
You estimated, so you take the level 1 feature, estimate the flow for it.
Yeah.
And then if you apply the, here what's happening is then you apply that flow. You apply the
next level
on the second level feature map, right? So you pick something from here, you applied the flow to predict, to predict the flow for, this level in the feature map, and then you apply the warp. So now this is time 1 and this is, let's say, time 2. Then these two levels are able to predict each other.
And then how would they go from, how would the warp, I thought the warp was applying to, the warp makes sense if it's the same dimensions, right? Because you have a set number of features and you're basically trying to shift the features in a certain way.
Yeah.
When you're going from a coarse layer to a finer grained layer, you're going to have a lot more dimensions, and perhaps even more features. Or I guess you would have more features. So how would you take the map from a coarse one and apply it to something with more features and more dimensions? I'm not sure if I'm explaining that.
Yeah, I see your point. So again, they didn't give as much details on the warp function. How does the warping operation happen? They did reference the paper, but I think it's pretty straightforward. I don't remember it the top of my head, but even if you remember, even if you look at this image, right here, clearly the resolution of this is different from the resolution of this, right? The resolution of this box is different from the resolution of this box.
Why do you say that?
Yeah, because let's say if this is size 10 and this is size 20.
Oh, okay.
This is size 30. This is size 20, right? So once you apply the warping operation, you are changing the resolution.
Okay. So we don't know exactly how it works, but it's standard.
Yeah.
To be able to do it.
Yeah. But it happens, right? So warping does lead to answer your question, warping does lead to change in resolution, right?
Okay.
Yeah, we know that's happening, right? As you go to higher and higher levels, this being male, the resolution is changing, right? Your boxes are the feature maps are becoming bigger and bigger.
Yeah.
So yeah, you apply the warp on level, apply this warp at level 2, then you get an estimate.
And then you get that estimate. Okay, cool. And then you're doing that the next layer, and then you're doing the same thing. So you're taking the, so this warp is, you're getting so you're doing the warp and then you're getting a regression and a loss. How does that regression and loss step work? How do you compare X hat, which is, I think, the predicted T+1 to the actual, you just run it through a model, basically.
Yeah.
Or something like that, right?
Mm-hmm. Yeah. Yeah.
Yeah, I guess how does how does that process actually work? So you have x hat to t plus 1, which is the prediction, then you have the actual x2 t plus 1.
Yeah.
How does that function work?
Yeah. So let's say you have a video, right? So you have 2 images,
Yeah.
time t plus 1.
Yeah.
So you take you run the JEPA encoder, which is this, and get different levels of feature maps, right? Then you take the image at time t plus 1, get different levels. You take the level 0, level 1, warp it, get an estimate, and then you take the image at time t plus 1. You already have the level 2, and then you calculate regression loss on the prediction versus the observation.
Okay. And then you just do it over and over again for each layer, and you calculate the sum losses.
Yeah. Yeah. And even though it might, they say in the paper there are only 6 levels, right? So it's not that deep, right? Like,
yeah. And then that would be one
regression loss.
And then that would be one flow. What would happen at that point once you've done this for one pair? Because this is all just like 2 frames, right? So you have 2 frames, you calculate the loss, and then what happens? The weights are adjusted. It's not like what happens after you go through this cycle.
Yeah. So let's say there are 6 levels and there are only 2 images. So you're calculating 12 regression losses. Right? So 2 images and like 6 levels. So actually there's only 6. 2 image gives only 6 regression losses. So you sum it all up using this formula into LREG, right? That's one component of the loss function. And let's just revise this slide here, right? So now we know how to calculate LREG, right? So in the multi-task learning, you have a video data set, you select a set of frame sequences, you select a pair of sequence, a pair of frames in a sequence, and calculate LREG. And every LREG is calculated with 6 terms, right? 6 terms for each level. Now, what happens where the LREG loss and the L reconstruction loss are related is, I'll go here, is like at the final step, at the final level, right? What happens is you take the flow estimate at level L, and now after warping, you can, and if you take the final flow map and you apply it to the input image at time t and apply warping on it, it should give you the image, how the image would look at time t plus 1.
Without any sort of, you're saying without any sort of convolutions.
Correct. Yeah. So here, then you have the final level, right? You take the finest feature map.
Yep.
You take that and then you kind of predict the flow using it. You apply that flow to your original image.
Yeah.
Right. And that should project and create the image for the next time step.
With all the pixels, all pixels, no correlations. And then that's the reconstruction loss. So that's the second component in the loss function.
Yeah. And this is also a photometric loss because you want the colors to actually match, right? Like they should visually look the same.
Yeah.
So that's what they call the reconstruction loss. So at the final step, you apply the flow map on the original image, get the reconstruction, get the second image from the video because you have that right in the sequence, and then calculate the reconstruction loss. And there are some details about it. I picked it up from this paper. I think they apply smoothing. Again, if you remember the related work part, they talked about it, like smoothing is useful. So they similarly add smoothing, and that becomes your reconstruction loss, right?
I'm assuming the reason to add the reconstruction loss rather than just using the reg loss is because you just want to make sure that the model is not overweighting for something that as convolutions. Like without doing this, without adding the reconstruction loss, perhaps it would be tough to get to actually process original input images.
It's like the reconstruction loss ensures that, in a way, it also remembers the semantic information, right? It's like it's learning and displacement, but they're making sure that they're actually learning the optical flow map, right? Because all the all the losses, all the other loss terms that are being calculated, these loss terms, the regression loss terms, they are not actually solving the optical flow task, right? The optical flow task says that if you have the flow map, then you can project an image to a new location, right? But the color values are preserved. Right? So the regression losses are not forcing the color values to be the same. Because they are being calculated at a feature map level. Right? At a feature level. But this loss is being calculated at a pixel level, at a color level.
Got it. Okay. Yeah, that makes sense.
Yeah, this way you know that your model is actually learning motion, right? Because then you can apply the flow on your original image and then create an image, create what's going to happen in the next frame. So now and because all this was still trainable, the encoder was still trainable, your MC-JEPA encoder has now captured motion information about the pixels because of reconstruction and regression loss.
Yeah. So just want to, or just a question on this. So theoretically, though, if you didn't want to include reconstruction loss and you just basically said, we're going to add an encoder and a decoder, whether it's or whatever, and basically said, we would take the initial image, and then encode it into one of those pyramids, right? Using a CNN as the kind of the pre-step or whatever, the encoder. Then you could get out the you would get the regression loss, and you could have another model decode that into the actual image, or would that not work? If you, I'm just curious, could you theoretically?
That should work.
Yeah, would work.
Yeah, that should work, right? But you're adding more parameters, right? Because till this point, remember, the warp does not have parameters. Only this has parameters, and f theta is being shared across different steps, right? The parameters are the same. I mean, it's the same model being reused. So you can use what you're suggesting. It just adds more parameters.
Yeah, it seems like way. I was just curious if it was possible. I wanted to check understanding.
Yeah, it's totally doable. That's what the reconstruction loss is doing, right? And remember, the pyramid was created so that it can the motion recognition can happen at a coarse level and at a fine level, right? So if there is a car here, right, the movement of that car would happen at a higher level in the feature map, versus like a movement of a leaf would happen at a more finer level, right? Because if at the lower feature maps or the higher feature maps closer to 0, they would capture more pixels, right? So that's kind of the idea. The reconstruction loss is happening at the pixel level, right? It's like you're now back to pixels. There is no pooling whatsoever. So this is again, we actually covered both training routines, motion and content. This is a quick view on what we have covered. We covered the content learning paradigm, which is like you pre-train on this, and then again train the same encoder model on the motion learning task. And this is kind of the new component here, f theta, which is a flow estimator architecture. The expander, as we talked about, it's a convolution architecture. So that's it. Here, there's an ablation study. I think I'll not go into that. for now, yeah. I mean, except maybe this graph basically talks about at what point of the training routine should they bring in the flow estimator, right? So as we talked about, there is pre-training involved. So initially they train the encoder only on images and then switch to videos. So this is the evaluation study they did to figure out at what epoch they should start the video training, right? And they found out that if you start it at the 10th epoch, so if you start training your MC-JEPA model on videos at the 10th epoch, there is the maximum gradient, right? Like you have the most benefit of reducing your loss. This is the cycle consistency coefficient, which basically tries to balance both forward and reverse warping. They also kind of fine-tuned it for 0.2 or did a hyperparameter search. I think this is the most important to understand, especially from a pre-training perspective. I think these are very formula specific. And again, these are covered by separate papers. They are only referred to them. So that's the ablation study in the paper. These are the final two applications which they have shown in the paper. So they have shown in the paper that if you take the MC-JEPA features, freeze them, and then use it to track how the pixels would move in a video, and then therefore recognize that, okay, these pixels belong to this person who's kind of moving forward. It does really well. And this is kind of the raw output of the optical flow map, right? So this is just freezing the features from the MC-JEPA model. This is running the MC-JEPA model and the flow estimator model to calculate the flow map, right? So these images are output of, not even this is the output. Sorry, this is the output. So this final flow map is being visualized here, right? And they're showing that it does really well, like MC-JEPA does really well compared to ARFlow, which is another top-notch model in optical flow estimation. And then they show that, for instance, tracking, if you just freeze the features from the MC-JEPA, you can track things really well, right? So that sums up the discussion. If there are any questions, we can talk about it.
Just the one question on the application of this. So a couple of videos that I was watching referenced JEPA. One was Jan LeCun. There was another one from the same channel about the applications in, I think, robotics or in video. They were talking about for generating video, you could use JEPA, I believe. And that, we talked about this last time as well. And to generate longer than, say, 3-second clips of video, they claim that you pretty much need to use JEPA. And I'm just curious how this would apply to longer form video. So one, just video generation in general, and then two, to longer form. Because the image, iJEPA, it was very clear how it could be applied to image generation, because you take a, one square of an image and you're, generating a bunch of other things. For generative, you're basically taking a masked image and you're able to generate, or, same thing with text. With this, it seems like it's focused, the discussion's been more focused on processing images over time rather than generating images. So I'm curious if you have any ideas how that translates.
Yeah, and so they don't talk about any applications of the features in generating images. They only talk about tracking, right? And they talk about being able to calculate the flow map. But I think it's going to be useful for generative models as well, because these features, right, essentially both MC-JEPA and iJEPA, right, they project images into some feature space, right, into an embedding vector. Now, MC-JEPA might be worse than iJEPA on image classification, on object recognition and all these tasks, but it's going to be better than iJEPA in tracking. And I would believe that should make MC-JEPA a better embedding model for for diffusion models. So if there is a diffusion model which generates images at the end, MC-JEPA would be a better input to it than I-JEPA, right? Because MC-JEPA will also give it information about how the pixels are moving, right? So even though they didn't, I think if we search, we'll find some paper which is using MC-JEPA features in a diffusion model to actually generate these images, right? Instead of just doing tracking.
Okay. Yeah, that makes sense.
Yeah, like a simple application, right? Like of the optical flow map is, when you're generating images inside a renderer, there are different layers of the images that you generate. There is like normal maps, diffusion maps, illumination maps. So some of these maps, can be directly generated from the flow map. So I think in renderers, where parts of the layers of the images can be generated really well with MC-JEPA, generating like a full video with, the final output, the visual image. They don't talk about it in the paper, but it should be useful. Any other questions? Yeah.
Yeah, the swag tools. So you're able to predict the T plus 1 frame from MC-JEPA. Could you iteratively use it to predict the further frames?
Yeah, it can be used to predict frames, right? Yeah, the features like the cosine distance between two adjacent frames in a video, that should be pretty low. So yeah, it should get you image similarity between videos much better than I-JEPA.
Oh, yeah, that's kind of interesting. So you should be able to predict the next frame, or the whole thing you're doing is predicting next frame. So you could do that repeatedly over and over and over again. Maybe not for a long sequence of time, but you can imagine something like runway ML. I don't know if they actually use this, but you can, because runway ML only does like a couple seconds of movement, right? You can imagine something like this being applied.
Yeah. I mean, here we are training on adjacent frames. So again, for long range, it may not work well. But I think if there might be a successive work on this, right? Something progressive where people kind of train it on more distant pairs of images.
Yeah, it would be interesting to see, because we're seeing a couple different things, right? We've seen, at least with images, the ability to understand the context of the image and basically take a small section of the image and then generate the rest of the image. And then you've seen here the ability to take one frame and generate the next frame. I wonder if you could, it would be interesting to see an application in a longer time horizon. How they would do that.
I think that could be a good idea for the next discussion, is maybe look at any papers which use MC-JEPA for video generation, or we can find something in video generation that uses embedding models. I think that those kind of papers would give us more insight.
Yeah, I think that would be really interesting. And then perhaps something, that could be really interesting. Maybe something longer. If there's anything that has longer time horizon, like multi-frame, I'd be really curious how people are doing that.
Yep. Yeah.
Because even if you go, say, 3 frames in advance, you're only gonna something like this is only, it really couldn't predict 50 frames in advance, right? Or
yeah, I mean, it's again, the FPS matters, right? So even if they're training it on 3 FPS images, you're talking about changes in a frame for every 300 milliseconds. And you can see that in Runway ML also. Runway ML, I think, generates videos of length 3 to 5 seconds. right? And that's
Yeah.
what the state of the art is, right? Like 3 to 5 seconds is what, 12 frames, 15 frames. And then you can always use an interpolation model in between. But that's where things are here as well.
It's short, but it's just something I heard in one of those videos that says this could be theoretically used for, for generating longer images, or longer videos, combined with the way that they do it with in IJEPA, where they say it's kind of like an arbitrary block and they're generating the other blocks. Like, is there a way that you could maybe take the I don't know. I'm just really curious about how you could actually use this.
Yeah, I mean, I'm sure there might be, that's like the idea worth trying. Again, the predictor model is not there, which is part of the IJEPA routine. It's missing here. So sure there will be a paper coming up which tries that.
Okay, sweet. Yeah, something like that sounds great.
Right. So end the discussion here.